Hello, I'm Ethan.
I'm Andrew. And I'm Robbie.
And this is the demonstration of our Bluetooth Low Energy Communication System. So we're going to just go through step by step to see how this communication system was structured, how the data was collected, and how we transmitted it, and then sent it up to the database. So the first step in our communication system was collecting data. So as you can see here, we used a little Arduino with this little joystick, and what's cool about this joystick is that it returns coordinates of its rotation. So you can basically twist it around and get different coordinates for where it's oriented. And so we use this Arduino script right here to collect that information. As you can see, we have the analog read-in for the X values, analog 2 read-in for the Y values, and then we're able to print those out. Once that's printed out, we can connect actually to Excel. So Excel has this great little thing called Data Streamer. Data Streamer is an add-on which allows you to connect to different kinds of, any kind of microprocessor, and if you want to stream data over it, you can do that. And so right here, we have the ability to connect to a device and stream information. So if I hit play here, I should be able to get information. It's coming up the screen as you can see. If I orient the joystick, you should see that the information changes. And so right now I'm taking about one sample a second. So right now what you're reading is the different coordinates on a coordinate system from 0 to 2 on both X and Y, both read in Excel right here in kind of rough real time. So what you can do here is that you can record the data using this button right here, and you'll be able to record a CSV of information, which you can then send to MATLAB. So for example, I can record here, I can stop recording, and what's awesome is that it just automatically lets you save a recording. And as you can see here, we've made a couple recordings already with the joystick, and we'll be able to see that in MATLAB as we go. So I'm just gonna stop the data and disconnect, and then we'll continue. All right, so now we'll move on to MATLAB. So as you can see in our workspace, we have a joystick recording, and that's what we use to actually process this information. So right here we have a little algorithm which converts our CSV to a table and then converts that to an array which we can then process. And we have a little check to make sure that we don't max out our information, because the maximum amount of PDU bits that we can send over is about 255. So we have a little check in here to make sure that we don't exceed those bounds and that we fit in the bounds that we need to. Now with that, we can go into the actual transmission part of our system. So one of the first steps is defining the PHY mode, which defines all the physical layer applications. So in this case, we're using LE1M. And then the next step is defining this config BLE transmitter. So these are all system level variables which we use to define our whole system. And this can be seen right here in this file. And it just has a bunch of different objects and variables which we use throughout. So the process of this transmitter, we start with configuring our PDU. So right here we have a object BLE data config PDU, and we just set a CRC initialization and then develop the data message which utilizes this object. Next step is using the BLE waveform generator to generate the waveform itself using the PHY mode and all the previous parameters. And to check this, we use a spectrum analyzer DSP object, which we can then use to see whether our transmission worked. And then the actual transmission itself, which we can see right here, where we, some notable things. So we have a radio ID, we connect to the Pluto, and we're using a center frequency that's within the channel data bounds. So we're using channel 35, for example. And then we define a couple more aspects like the gain, the frame, and the sample rate. And then we create our SDR transmitter object. And then once we create that object, we're able to call it with our waveform. As you can see here, we're just continuously transmitting the waveform so that at the receiver, we'll be able to receive that. And with that, we'll send it right over to my buddy, Andrew.
All right, thanks, Ethan. So once the data is received from the transmitter, we're going to begin on this side. So first, we're going to start by looking at the physical mode, which once again we specify to be 1 megabit per second, and it's once again going to use the same configuration file that is being used on the transmitter side. From there, we're going to proceed over to set the radio object, setting parameters such as its center frequency to use, which is the same as it is on the transmitter, to ensure that the data properly is received. the number of samples per frame, which is going to denote how many samples we receive from this transmission. And then we're going to set up the spectrum scope, which is going to allow us to see the power spectral density of the signal that we just received. All right, so proceeding a little further down, we're going to begin to talk about the actual flow of the code. And so first, this begins by, once the signal is received, we've got the AGC, which is the automatic gain control, which is going to help mitigate any deficiencies that might have been a result of noise from the channel, whether a signal got boosted in some areas or severely diminished in other areas. From there, we're going to proceed over into a frequency compensation, which is going to help correct for any frequency offsets that might be occurring between different clock sampling frequencies of the two Pluto objects, which aren't always the same. And then from there, we're going to have the preamble detector. The preamble detector in this case is going to be looking for the preamble specified by the 1 megabit per sample method, which is a 010101 pattern, 01. And then from there, we're going to begin to collect the data. Once again, we have the AGC being set right here, the DC offset, which is going to be corrected for, which helps to compensate for any shifts that might have been occurring in the data, the preamble detection after the frequency compensation, and the Gaussian match filtering, which is done on the transmitter side, which helps to ensure that the data is successfully sent across and encoded. And then from there, we're going to proceed over into the 5-bit recovery, which Robbie will discuss right now.
Sure. So the first step with the 5-bit recovery is that we need to be able to take in the correct index of our data at which the preamble is located. In addition, we want to be able to take in our packet count and CRC count. So if we move out back to the receiver, I'm going to go back there real quick. So these things are taken in, all of our data after the Gaussian filtering is taken in, as well as our packet count, as said before, and the index at which the preamble is located. The primary reason for this function is to output our payload data from each individual packet. Inside of this function, the preamble is detected. It is confirmed to be the correct preamble that we are looking for. And then once that happens, and the verification happens of the access address of the packet as well, then the payload data is outputted. So, moving back over here. Once this payload data is outputted, we can then move into post-processing, during which we do a little bit of reshaping and formatting such that it can be processed correctly. In the next step of this, once we gather all our final data that was transmitted over from the joystick, we move down into the ThinkSpeak interaction. So, ThinkSpeak is a service that allows us to send data and visualize data through graphs. It particularly is nice because it allows us to show the timestamps of the data that were sent. So the data is first processed into a table. This table has two columns. The left column is the x-axis data that we collected, and the right column is the y-axis data that we collected. The fact that we send the data over in two columns allows ThinkSpeak to know that we want to process it and display it in two separate fields. So in ThinkSpeak, we can graph things in multiple ways, and if we want to transmit, we can show that we can display our data on two separate field charts.
So right now I'm transmitting on the transmitter. I'll let you know once it's ready. We should be able to see in the command line in the spectrum analyzer on the receiver that the information was received.
Okay. So that's the spectrum right there. Under the command line, we see the data values. Right now, this is the channel right there. So as you can see right there, with the updated information.
We have our data points.
There we go.
So now, our receiver will be continuously sending new data points to ThinkSpeak on intervals of 15 seconds, as that is the allocated time that ThinkSpeak needs in order to process correctly. So every so often, we just saw it, that a new data point will be present in the graph.
Cool. Perfect. Thank you so much.